The essence of developmental continuity is that experience plays a role in the development of later behavior patterns. So that's what we're going to be looking at explicitly in this segment. So what is experience? Probably the simplest definition, it's all encompassing, which is generally a good thing, is sensory and or motor function. Anything that causes the sensory systems to operate, to send action potentials back to the brain, and any motor activity, movement that you engage in. These are all forms of experience that begin prenatally and can affect behavior throughout your lifetime. So, what kinds of experience are we talking about that can influence behavior? Well, two general categories. Experiences can either be linear or nonlinear. So, what do we mean by that? Linear versus nonlinear. Linear experiences are quite obvious and nothing that you'd have a hard time making a connection with in terms of the development of later behavior, whereas nonlinear experiences are non-obvious or less obvious or subtle, things that you might not necessarily think could possibly affect the development of a particular later behavior. So yeah, linear things are pretty much out there. They're in your face. They're obvious kinds of manipulations that experimenters might do to see the effect on later behavior. Whereas nonlinear, you might wonder, well, how did you even think about doing that in the first place? Because it just seems that those kinds of experiences would be so distantly removed from the development of what you're actually studying later on. Nevertheless, both of these things play a very important role. So let's look at some nonlinearities. For example, can your baby's odor alter auditory cortical neurons? Odor, olfactory, altering auditory cortical neurons? Well, turns out that if you are a rat, that can happen, because that's the experiment that was actually done to look at this. So what you'd expect if this were a linear type of experience is that early vocal auditory experience would affect the development of neurons in the auditory system, something like this. Well, and that wouldn't be surprising, and who knows, it might very well play a role. But nonlinear would be something like rat odors. So yeah, in this study, they found that exposure to pup odors actually affected the cortical auditory neurons in rats at a later point in time. Comes from this article in the journal Neuron. Multisensory integration of natural odors and sounds in the auditory cortex. In a way, it's not all that surprising because everything is interconnected in the brain, to some extent at least. But again, it's not the kind of manipulation that a person would necessarily jump to if you were interested in studying the fine-tuning of auditory neurons in an adult. You'd probably look more toward auditory experiences early on. But of course, here we see that if you look at odor experiences, smelling the pup odor actually does affect the fine-tuning of auditory neurons in the adult rat. Here's another example of a nonlinearity. Can your diet affect fear? Really? Well, if you are a squirrel monkey, absolutely correct. Now, a linear experience would be, if you have a bad time with snakes early in life, then you're going to become afraid of snakes. Because squirrel monkeys do have a species-typical fear of snakes. They just don't like snakes. Well, that would be a linearity, and I'm sure that if you gave young squirrel monkeys experiences with snakes early on, that yes, they would have an ultra fear of snakes later on. That's not what this study did. What they did was to look at diet. So, a species-typical diet for a squirrel monkey is a mixture of insects and fruits and things like that. Well, it turns out that if you give them that kind of a diet, they will in fact develop their normal species typical fear of snakes, or even snake-like objects like snake models, and even rubber hoses were used in this study. However, what they did find in addition to that is if you remove the insects, they do not develop a species-typical fear of snakes, which would be an abnormality for the species because it is a species-typical fear. So basically, they need to have a varied enough diet that includes insects, which they normally would be eating, in order to have a normal developmental timeline fearing snakes. And that study was done by Masataka back in 1993. Can seeing your feet affect your ability to eat? What? What, does that make sense? It does if you are a chicken. So here's what was done here. Again, a linear experiment would be if you give chicks an experience with manipulating mealworms and eating them, that they'll have a very easy time picking them up and then swallowing them. Okay, well, not a big surprise, and that's not what this study was all about. What it was all about was early on, take some chicks and put them in different conditions and see whether or not it affects the ability to pick up and manipulate mealworms, which is, by the way, a preferred diet for a chicken. So what they did was to give the chicks booties so they couldn't see their feet. There was a control condition where they wore booties where they could. But if they couldn't see their feet, they had a really hard time picking them up. And even if they picked them up, they would typically drop them before they had a chance to eat them. So seeing your feet, if you're a chicken, does play a role in your ability to eat what becomes a very highly preferred diet a little bit later on. So this minimal visual restriction greatly affects the ability to respond appropriately and act appropriately upon mealworms. So those are some examples of nonlinearities. So, if we're looking at developmental outcomes and this spectrum of experience ranging on this continuum from linear to nonlinear, most obvious to least obvious forms of experiences, well, all are going to play a role in the development of species-typical behavior. It's just that people have never thought so much to look at the nonlinearities because they are subtle. So how do you even know where to look? So, sometimes you just have to start thinking about the normally encountered kinds of experiences that animals have and see whether they might be non-linearly related to the development of something else. And maybe they will and maybe they won't. But it's very interesting to try, and even more interesting if you get a positive result. So with that in mind, let's look at roles, specific roles of experience in the development of behavior. Actually, we can broaden it, development of behavior in the nervous system, really, but we'll focus more on behavior. So roles of experience, how can experience work to affect the development of later behavior, whether those experiences are linear or nonlinear? So there's a number of roles. The first role is what's called maintenance. So with maintenance, experience sustains or preserves a previously developed outcome. So you have some developmental outcome that was probably affected by other things. Okay, it's there. But now the experience is necessary to keep it there. Without the experience, it'll go away, it'll deteriorate. So experience maintains behavior. So we can look at it graphically like this. So we have level of development, a low level of development and a high level of development over developmental time. So there is our developmental outcome. It's already there. It's highly developed. There's the onset of experience. So with experience, it will remain developed. But without experience, it will go away. So if you can do a study that shows that this is the situation, then you can conclude that experience maintains behavior. So you take some kind of a behavior that's already there and then take away an experience, whether it's linear or nonlinear, and then see if that particular experience was in fact necessary to maintain behavior. So let's look at an example of this using a visual cliff. Okay, so this was developed for studying human infants. And by the way, it's not a real cliff. The kid's not going to fall off the deep end. It is, remember, a visual cliff. It is a visual phenomenon. So there's a shallow end where the kid is on right now, and then a deep end, but there's a glass that covers the deep end that's adjacent to the shallow end. So it's really one solid surface all the way across this this box. So mom puts baby, baby likes the shallow end. But, you know, visually it looks like a cliff, even though the kid's not going to be falling anywhere. Otherwise, I don't think mom would put put the kid there in the first place. But you can see kids really fearful to some extent about going over that deep end, even if mom calls it. Basically, this was done to see if depth perception, or when depth perception kicks in kids. And if they don't go over the deep end, then you can see that they perceive depth. And if they do, then depth perception has not yet fully developed. So in these kids that we're looking at here, it is fully developed. They won't go over there. Okay. By the way, animals have been put on this device, and we're going to be looking at an animal study, not these animals, though. So there's a cat, there's a kitten, and it's a Siamese, long-haired Siamese. It's not going over that deep end. It obviously perceives depth. Now, a mountain goat, that's a young mountain goat, that's an interesting situation. They're not going to go over the deep end, but they're going to do what mountain goats do in the wild. They're going to walk on the ledge. There's a little bit, enough of a ledge there that it can actually walk around there and get over to the deep end without walking over the glass. And of course, in the wild, these guys live on very steep cliffs with ledges that may be as small as that or maybe a little bit larger. So it's just doing a species typical kind of thing. No way the cat would do that. So the study we're going to look at was done by Richard Tees in 1974, and he used a specially modified visual cliff where you could actually move the bottom, the floor pattern plan, over on the left to become adjacent to the shallow end, and then gradually, inch by inch, move it down or move it up to see if rats are in fact discriminating depth. And he did this in two different conditions: rats that were either reared in the light or reared in the dark for varying periods of time. So he was interested in seeing whether light is necessary to maintain, again, we're looking at the maintenance role, visual depth discrimination. So here's his my drawing of what he did. So there's a deep end and a shallow end, but initially the deep end is shallow, and then he can gradually lower it inch by inch in different conditions. Bring it back up if he wants to. And see at what point a rat will refuse to go over that deep end. How fine a depth discrimination does the rat have before it will be fearful enough to not walk over the deep end? So here are his data, which also kind of explains how he did this. No rat was tested twice. These are all independent groups. So he's looking at rats at different ages. So the youngest age is 20 days of age. So he has dark-reared rats, those will be red, and light-reared rats, that will be yellowish, orangish, brownish, okay? So notice that initially they start out at the exact same point of differential depth discrimination. So basically, when he lowers the deep end to about, I guess it's 7.5 or 8 inches below the shallow end, that's where they will refuse to go over to the deep end. So on this graph, the lower values mean better visual discrimination, means better depth perception. Okay, so make sure you're aware of that. So that's not bad. Then he had rats that had been reared in the light or dark for 40 days and then tested them. So remember, these are different groups of rats. The only way you could do this experiment. Well, the dark-reared rats stay where they were at 20 days. The light-reared rats are starting to get a little better in their depth discrimination. Notice that at fewer inches, maybe about, 4.5 maybe, that's when they'll refuse to go over there. They see that now as being deep. So they're saying at 4.5 inches, no way, I'm staying on the shallow side. Okay, 60 days. So they're running in parallel with one another. But notice that the light-reared rats are indeed better than the dark-reared rats. 80 days, they both taper off at about, I guess that would be about 4 inches or so. for the light-reared rats and maybe about 6 inches for the dark-reared rats. And at 100 days, the light-reared rats just a hair better at differential depth discrimination. But look what's happening to the dark-reared rats. So again, rats that were reared in the dark for 100 days are now getting worse. And we can just follow this out. They continue to get worse. They continue to get a lot worse the longer they're reared in the dark. The light-reared rats, basically that's the control group, the light-reared rats, are basically at asymptote. They're doing really, really well in terms of their fine level of depth discrimination, whereas the dark-reared rats are not. So, yes, light is necessary to maintain the fine discrimination of depth that rats showed at the beginning of the study at 20 days of age. Okay, our second role of experience is called facilitation. So by facilitation, we mean that experience has a temporal effect, such that development is earlier or faster. It's going to develop anyway, so don't get confused about this. If the role we're talking about is facilitation, it will develop. It'll just take longer for that to happen, or it'll happen at a later age. Well, that's the same as longer, actually. So ultimately, they'll catch up, or just about catch up, but they won't do as well as the animal that has had the experience. So again, here's our prototypical graph, and we'll look at how that would map out. So now you don't have something that's already developed, okay? It's undeveloped. Here's the onset of experience. So what's going to happen with experience? It develops quickly. But without experience, it doesn't. It takes longer to develop, but it does develop. So basically, experience is facilitating development by making it happen earlier or faster. So, examples. An incubator. Incubators are dark. Why? Nests are dark, so that's fun. It turns out, though, if you turn a light on in an incubator and you're incubating chicken eggs, the study was done with chicks, though in this picture you're looking at duck eggs because that's what I had in my lab. That's my incubator. Chickens will hatch up to 24 hours early if you turn the light on relatively early in the incubation period. Just put it on for about a day, just 24 hours. And that will cause the chicks to hatch about a day earlier without any noticeable devastating effects on anything. So experience facilitates hatching. I mean, they're going to hatch anyway at the normal time. It's just that with the light, they'll hatch at an earlier age. Hatch synchrony in bobwhite quail. So this is another good example of facilitation. So there's a real quail nest, bobwhite quail found in North America, and there's a quail with chicks. Now the thing about quail, look at the nest. Well, actually, this would occur in just about any nest of any species. Nests are concave, meaning the eggs are going to physically touch one another. Now, the embryos do start to vocalize prenatally. We've looked at that in another segment by looking at duck embryos, and it's the same case with any bird of a what we call a precocial type species. I was about to say altricial. Precocial species, and maybe in some altricial as well. Precocial species are ones that at the time of hatching are pretty well developed, like we see here with quail chicks. So basically, they're vocalizing inside the egg. But quail chicks, bobwhite quail chicks, in fact, I think Japanese quail chicks as well, do something rather interesting, additional to vocalizing. They make these passive clicking noises in the respiratory system. And that's what they look like. This is what they sound like. So it is a sound, but it's really being produced more by their breathing rate and things like that. It almost sounded like a heartbeat, but it's not the heart that's causing that. Well, if the eggs are physically touching, the sound will transmit from one egg to the egg that it's touching. So there is communication going back and forth between the embryos in terms of these clicking sounds. So here's what a researcher named Margaret Vince, V-I-N-C-E, did in Cambridge, England. So she had an incubator and she had different clutches. Now, a clutch means that is like one incubator tray full of eggs, and because incubators will hold a whole series of trays. And in each tray, she had some eggs that were touching like they would in a natural nest, and then others that she pulled apart so they weren't physically touching one another. So the ones that were touching will be designated in blue. Every blue dot is a different egg that was touching another egg. And the ones in yellow were not in contact with one another. So if we look at our first clutch, notice when they're hatching. 0, down at the bottom, that is the average hatch time across all these clutches. In other words, when they should be hatching. So we're going to look at all the clutches, and as we go along, I think you can easily see what's happening. The ones that were in contact, the blue dots, and again, every dot stands for an egg when it hatched. The blues are clustered much more closely together in terms of their hatching time than the yellows that were not in contact, that are spread all over the place. Some are hatching early, some are hatching around average, some are hatching really late. And so it turns out that this clicking vocalization is something that in fact synchronizes hatching so that the eggs hatch at about the same time. They will hatch anyway, as long as it's a healthy embryo. They'll hatch anyway. But this clicking actually facilitates hatching by making sure that the ones that might be a little bit delayed developmentally are sped up so that they're hatching around the same time, which is important because the hen is going to call her chicks off the nest, and if there's any that have not yet hatched, they're going to be left behind. So basically, it's accelerating hatching. And the reason we know it's accelerating hatching is from another experiment that Margaret Vince did involving 3 different incubators. Or they could have been 3 different trays in the same incubator. That would work too. So, because the trays are physically separate. There's no communication going from tray to tray. So she had a bunch of eggs, and she just, they were all touching one another, okay? And so she put them in one tray, and they hatch, that's when they hatch. And so that is the dashed line is the average hatching time for that clutch. So we're designating that down at the 0 point, down at the bottom. Then she waited 24 hours to set the eggs in another tray, wait a day, and she put them in, and they hatch exactly what you'd expect about a day later. Okay. Now, what she did to create her third group was, well before hatching, she pulled an egg from group A, day 1, and an egg from B, day 2, to create group C, where she put those eggs together, touching one another. She paired them. And look at the hatch times. So remember, the blue egg touching a red egg, even though they're all white, but you get my drift. Here's when they're hatching. And pay attention to those blues. So notice all those blues are hatching much earlier than the blues that were set a day later. They have accelerated their hatch time by being paired with a more fully developed embryo, more fully developed by a day. And it turns out that yes, it is the clicks of that earlier group that actually sped up the hatching time of the blue eggs. And notice there was no delay in the hatching of the day 1 red eggs. They're hatching right around the same time, the average time for day 1. So it's not that the blues are holding the reds back. No, it's an acceleration, not a deceleration effect. So it's a speeding up of development. So yes, the clicks are facilitating hatching time by making it happen earlier in these eggs that were set in the incubator a whole day later, the blue eggs. Okay, our third role is called induction. So by induction, we mean basically experience is kind of necessary or else something's not going to develop. So experience channels development in one direction rather than another, or just simply makes it develop in the first place. Another aspect of this that I guess we're not going to consider as much because there's fewer examples, I think, is that it can enhance the specificity of a partially developed behavior type system. So you have something that's not fully developed, it's partially developed, but another aspect of the inductive effect of experience is that it would bring it up to speed. It would make it a lot better. It's not a facilitative effect because without the experience, it would remain in that relatively undeveloped state. Okay. So basically, if you want something to develop, then experience is absolutely necessary for that to happen. Without the experience, it will remain undeveloped. And so we can graph that out like this. Undeveloped. Onset of experience. Experience begins. With the experience, something develops. Without, it does not. So experience, if it's an inductive effect, is necessary. So here's a good example. The way you handle mice can induce anxiety if you mishandle them, because different researchers have different ways of handling mice, and some are a lot better than others. But, for a long time, people weren't sensitive to this. I mean, the easiest thing to do if you're trying to capture a mouse from a cage is to grab its tail, okay? So that's what's being done here. So the guy's just grabbing the mouse by the tail. There's the first session on the left, okay? Just holding it gently by the tail, not being mean to it or anything. But then look what happens 9 sessions later, after he's been doing this every day. The mouse is actually showing high anxiety and avoidance of the guy. He moves away from the guy's hand, even though the hand isn't doing anything, not reaching for the mouse. That mouse just doesn't want to be around the guy's hand. What if you do what's called tunnel handling? So you gently put the mouse in a tunnel, and so you're not messing with the tail or the mouse other than the fact that it's in this glass tunnel, and then you let it go. So you do that for 9 days, and then on the 9th session, you hold the glass, and the mouse comes over. Low anxiety. It's not afraid of the glass. It's not afraid of the guy's hand. It goes right into the glass. There's no avoidance whatsoever. Very low anxiety. So obviously that's better than tail handling. What else can you possibly do? Cup handling. So you cup your hands gently and just hold the mouse gently. You're not messing with the tail, just holding the mouse, let it crawl around your hands. You do that, and then 9 sessions later, you just put your hand down into the cage, and the mice come right over to it. They're not afraid of it. Again, it's another low anxiety condition where they're glad to approach your hand. So basically, you can see that tail handling induces anxiety. I mean, otherwise they're not afraid of you. But if you grab them by the tail, then they are. So that is not the best way to handle a mouse. It might be the easiest way, but it's not the best way. Otherwise, you're going to end up by inducing, remember, we're talking about induction here as the role of experience. You'll end up with inducing a high level of anxiety and active avoidance. And that can affect whatever behavior you're studying, obviously, because it's also affecting the hormonal system, the stress hormones, things like that. So these are the best ways to handle a mouse. You can either put a glass tunnel in there or just cup your hands and let the mouse come to you. Learning. Almost any form of learning would be a form of induction, because unless you have the experience that enables you to learn something that you didn't know before, well, it will remain undeveloped. So basically, any form of learning would be a form of induction. I'll just use tool use as an example, though. So here's our good friend, the New Caledonian crow. Love that bird.
This grub has got big jaws, and if attacked, it can give a powerful bite. And that's what the crows rely on.
So yeah, I mean, we've seen examples of this in the laboratory in different segments, but it happens in the wild. But they still have to learn to do that. I mean, it's not going to automatically just happen. So they basically trial and error. If they can get the grub by poking at it with a stick, then they'll be able to get the grub, and without doing that, they won't. And so basically, any form of tool use is something that would be an inductive form of experience. You learn to use a tool to solve a problem, and now the problem is solved. So you have now learned, this experience has induced the behavior that the next time you encounter that problem, you'll go get that tool. Ah, there I am with a glass of water. What I have here is a glass, and there's water this high in the glass. I put a paper towel at the bottom for reasons you'll see in a second. Floating on the surface is a piece of food, but suppose I cannot reach the food because the water level is too deep. Well, suppose I'm presented with some objects, some rocks like this. If I'm really clever, I might be able to figure out that if I drop a rock into the water, watch the water level, aha, it'll go up. And if I'm really clever, if I have a choice between a large rock and a smaller rock, the larger rock should bring the water level up even more. And now I can reach the food. That's the task that a New Caledonian crow was faced with. But it was even a little bit more complicated than that. Oh, and the reason for the paper towel is so that while I'm filming this, the rocks would not shatter the glass. Which, of course, is something I learned. So that was an inductive form of experience as well. And by the way, don't drop the rock in your lap, for God's sakes. Okay, so we've seen experiments kind of like this. I think this is one I may not have showed before. It's a little bit different because we're dealing with two types of cylinders here. So there's our crow. It's got some objects. And it has a choice of a wide cylinder and a narrow cylinder. And the water levels are the same, and there's food floating at the top of each of them, but it can't reach the food with its beak. So what's it going to end up doing? Tries the wide one and realizes it still can't get the food, so it's going to go to the narrow one and needs one more. Yeah, one more. Going to again stick with the narrow one. It brings the water level up to a higher level than the wide one did. There we go. There goes the crow. Okay, so an inductive form of experience. Siblicide actually is a species typical behavior in some species. I mentioned it in an earlier segment when we were looking at hyena pups and the fact that they have well-developed canine teeth. And basically, the strongest one in the nest is the one that in the nest. I guess it's a nest, isn't it? I don't know where hyenas give birth, but the birthplace of the hyenas, it's the survival of the fittest among the pups. The one pup is going to try to kill the other pup, and that will in fact happen. It's called siblicide. Okay, because they're killing one another. The kids are basically. So we're looking at two species here: great egrets and great blue herons, both shorebirds. Now, siblicide is a species typical behavior in great egrets. It's not in great blue herons. So it turns out that in great egrets, what the parents do is bring small fish back to the nest so that each individual egret can actually monopolize its own fish. So each one gets a fish, that's mine, you stay away from my fish, kind of thing. With great blue herons, which are non-siblicidal, the parents bring larger fish back to the nest. So each of the chicks has to share a larger fish. So they learn to share early on. So I think you can see where this is going, okay? Now, what was done in this experiment was to do some cross-fostering of the chicks. So they had a great egret nest, right? But they reared heron chicks in it. Great blue heron chicks are now put in a great egret nest. And they did what the great egrets do. The parents are still doing the same thing. they're feeding small fish to the heron chicks. So now each heron chick has its own fish. They became sibblicidal. So monopolizing their own small food item induced, we're dealing with induction, remember, induced sibblicidal behavior, which remember is not species typical for the great blue heron. So it had to have this experience of monopolizing a small fish to have that effect. By the way, what happened with the egret chicks, because they had to swap nests, and so the herons are now rearing the egret chicks. So the herons are still bringing back to the nest what they would bring for their own chicks, where they had to share a large fish. So what happened to the chicks? They were still sibblicidal. But remember, for great egrets, it's a species-typical behavior, and it's very difficult to undo a species-typical behavior. So it had an inductive effect for the heron chicks when raised by great egrets, and things did not change for the egret chicks reared by the blue herons. Well, our fourth and final role of experience is called predisposition. It's very much like induction, but with induction, basically it's one form of experience that induces the behavior. With predisposition, we're dealing with two different experiences that are necessary for something to be induced. So basically, one form of experience predisposes or primes the organism for being susceptible to the second experience. It would look like this on our graph. Something's undeveloped, and we have the onset of the first experience that remains undeveloped. Okay? Now we have our second experience, and now it develops. And without that second experience, it remains undeveloped. Okay? So, ferrets, good example of that. Prenatal estrogen exposure and postnatal testosterone exposure are both necessary for normal sexual development when they get older. If you give them the prenatal estrogen but not the postnatal testosterone, you'll have abnormal sexual development. If you take away the estrogen prenatally, only give them the testosterone, which you think, well, that should be enough. I mean, that's a sex hormone, testosterone. Actually, so is estrogen. But that's so early in development, you might say, well, that doesn't matter. Well, it actually does. Take away the prenatal estrogen, only give them testosterone, still abnormal sexual development. Both experiences are necessary. So somehow estrogen is predisposing the ferret to become susceptible to the influence of postnatal testosterone for normal sexual development, predisposition. Here's an example with mice that are going to be cross-fostered. We have two different strains of mice, B6 and BALB. Okay. They behave very differently. They've been bred for different purposes. And we're not going to worry about the specifics there. It's just that there's differences in learning, open field exploration. An open field, a big open arena. And if they don't explore, they hug the walls. And if they explore, they go out in the middle. And we've seen examples of that in other segments. And anxiety levels. And it doesn't matter which strain does which for the purpose of this example. So again, two strains of mice, B6, BALB, with a variety of different types of behaviors. So what they did, they took B6 embryos, okay? And prenatally, they could do implantations. So what they did was take from a mom or moms B6 embryos and implant them either into other B6 mice, it's sort of like the control condition, or into BALB mice. So the prenatal experience for all the B6 embryos is to be with a B6 mother, not your own, but another B6 mother, or the mother of the other strain, BALB. So that's experience number one, prenatal. Experience number two is postnatal, because after birth, they then reared them differently. So the B6 ones that were prenatal with B6 were postnatally reared by other B6 moms, okay? They always did different moms just as a control, okay? Now, they also had a group of B6 prenatally incubated mice. That's, yeah, figuring out a way to say that. And had them fostered with BALB mothers. Okay? Now, they did the same kind of thing with the mice that were prenatally reared by BALB. So they took some of those and gave them to B6 moms postnatally. So they're out of the BALB experience now and back with their own strain. And they took some that they just reared with other BALB moms. So those guys had BALB prenatally and BALB postnatally. So you see what's going on here? I think it's pretty clear from the drawing. So let's look at the behavioral outcomes here. So the first group, B6 all the way, B6 prenatal, B6 postnatal, they showed the B6 behavior patterns. What about the B6 that had prenatal experience with B6, but postnatal experience with BALB? What did they do? They still had B6 experience, B6 behaviors rather. Okay, B6 with prenatal BALB, but postnatal B6 still behaved like B6. Well, you can see where we're heading with this now. The ones that had prenatal experience with BALB and postnatal experience with BALB behaved like BALB. So the induction of BALB type behaviors took two forms of experience, both prenatally and postnatally. Prenatal alone would not induce BALB behavior. Postnatal alone would not induce BALB behavior. They had to have these two different experiences, prenatal and postnatal, with BALB in order to subsequently behave like BALB mice. Predisposition. So, what can we conclude from all this? Well, first of all, obviously going back to linearities and nonlinearities, they all affect the development of instinctive behavior. And we saw from our roles of experiences that these can operate in very different ways. So that's pretty much what I wanted to say about experience and its role in the development of behavior.